Vilas. Okay, good morning to everyone. Can you hear me, yeah?
Yes.
And can see the slide, right? Can,
Yeah.
eh? Okay, thanks. Okay, class, so when is your last lesson? This Thursday, right?
Thursday.
Thursday, right?
No.
Okay. Thursday, right? Thursday is your last lesson for this semester, right?
Yes.
Okay, so Friday we will have one extra, the replacement at 10 o'clock. It's fine for everyone, right? So any concern, just write it in the WhatsApp. Okay, so let's start with the next topic. Next topic is going to be oscillation. Okay, it's about oscillation. So this is going to be uh, every year. Every year, I think paper four, your A2 paper. In A2 you have about 16 topics, but the amount of questions going to come out is around maximum is 12 structured. Okay, 12 structured. So 16 topics, 12 structured. So that means not all the topics will be come out in exam. Okay, some topics will come out maybe 3 years once. Some topic may be alternate, but some topic every year it will be there. So such topic like that, such like that is one of them is oscillation. Okay, this topic. This topic every year you will have a question. Gravitation circular together will be a question every year. Okay, temperature very rare. Ideal gas, most of the time is there, not every time. Thermal also like that. Most of the time will be there, but not confirm every time. But oscillations always is there. So good to study. Okay. So oscillation is the basic of wave. Okay, oscillation is the basic of wave. How wave is produced, how sound wave is produced, how radio wave is produced. All the what you call the fundamental movement is a type of oscillation. Okay, something oscillate create the wave. Okay, so this need to be done, but for A levels, after you learn wave, then only we done the oscillation. We are doing the oscillation, the fundamental. Okay, let's move on. So these are the learning outcome. Something called simple harmonic motion, simple harmonic oscillation. We're going to talk about energy in oscillation, and we're going to talk about damped and finally resonance. First, what is meant by oscillation? So oscillation are back and forth movement. So back and forth movement. Okay, oscillation are to and fro motions. It's called oscillations. Okay. So could be the wave produced by an oscillation. A pendulum, spring. Okay. So you see in the wave, the particle going up and down is a type of oscillation. Okay. Okay. The character of oscillation. Okay. Oscillation have some character. The main character of an oscillation is that it's periodical. Okay. It has a period. Every oscillation will have a period. Okay. So you see this graph here, sinusoidal oscillation, random oscillation. Another one is a square wave oscillation. All type of shape will have a period. Okay, so it's a period. The motion repeats itself at a regular time interval. The shape of the displacement time graph may vary greatly, but each motion repeats with the regular time period. Yeah, we got a different pattern, but the pattern we're going to focus in your syllabus is the sinusoidal. Either going to be a cos graph or sine graph. Okay, the displacement versus time. That's our syllabus. Okay. So oscillation, the properties of oscillation similar as wave. Okay, similar as wave because oscillation is the source of wave. Okay, the four properties the oscillation will have is this four, which is similar as wave. The oscillation will have its own amplitude, will have its period, will have its frequency, and now it also have something called angular frequency. Angular frequency. Angular frequency also omega. Last time in circular motion, you call it as angular velocity, angular speed, angular velocity. That's for circular motion. This called angular frequency applied for oscillation. Okay, how many radian it travels per second? It's called angular frequency. Same formula, everything same, but in oscillation we call it angular frequency. Okay, so 2 pi over t omega equals to 2 pi f is used back. So an oscillation, bigger the amplitude, more energy the oscillation has. Period, greater the period, smaller the frequency. And greater the period, omega become smaller. So one example, the spring is oscillating up and down. Spring is oscillating up and down. So let's say we start the time when it's at the equilibrium, we start the time. When it goes up, on the way it goes up, we trace the graph. Okay, time started when it's in equilibrium, on the way it's going up. This is how the displacement versus time graph going to look like. Okay. So from this graph, we can obtain the four properties. So what is the amplitude, period, frequency, and angular frequency of this spring oscillation? So I think it's easy for you to deduce because we've done this before. It's like a wave. So amplitude is 4, of course. Period is 10 seconds. Frequency is 1 over 10, of course. And omega is, you can use 2 pi f or you can use 2 pi over t, 0.63 radian per second. Okay. The unit for omega, of course, the same unit as you learned last time, radian per second. Okay, but we know radian is dimensionless. Okay. Okay, now phase difference. Oscillation also has its own phase difference. Phase is different. For example, you see this graph, two types of oscillation has been traced here. When the time is zero, maybe the orange color, maybe the spring is time is started when it's at equilibrium. The blue one, I think the time started when the spring is at the compressed state. Okay. So when the time runs, the first spring, this is your A, this is your B. A, B. When time runs, A will go up first, B will come down. So then so there will be a phase difference, there will be a phase difference. They have a different phase. They move around rhythm, what do you call, with a different phase. So how do you find the phase difference? The phase difference, same as last time you learned in your wave. What is the formula to find phase difference? Anyone? How do you find a phase difference? The crest and crest separation. If it's time, so you put it, if it's omega t is in terms of theta, here they put omega t is actually theta. Theta, sometimes it will be in terms of time. Okay. Sometimes it will be in terms of distance, but normally in oscillation it will be in terms of time. If it's in terms of time, crest to crest, check the time interval how much, t. Then how do you find the phase difference? Same formula like last time, right? Right on the top. The phase difference is what? T over what? Period times 2 pi. You get the phase difference. Okay. So recall it back, same as wave. Find the time interval between two crests or time interval to any identical points, two identical points. Trough also can. Okay, find the t over the period times 2 pi give you the phase difference. Okay. I have to tell something about phase difference. So let's say you have one spring is at the bottom. Okay, this is your equilibrium. This is your origin. Okay, it's at the bottom. Another spring in a compressive state. Okay, okay. So this spring going up, the other spring is going down. Okay, so they always travel in opposite direction. Okay, when this spring is up, the other spring is down. Okay, so what is the phase difference between these two oscillations? Anyone? What is the phase difference between two oscillations which is always travel in opposite direction? So A and B. So if you plot a graph, for the case of A, because it has at a negative displacement when the time zero, this I put time zero, the A is at the negative displacement, so it has a bottom here. So A will trace a graph of what? It will trace a graph of negative cos, because it starts at the negative here. So this is for your A. How about B? B start from the positive displacement on top, positive displacement. So B will take a cos graph. This is for the B. So what is the phase difference between A and B? Anyone? So can you see here? You take crest and crest. You know lah, cos and negative cos. What is the phase difference? It will be 180 degrees. Or you can say how many radian? It's pi radian. It's pi radian. Any oscillation moving opposite direction is a pi radian of phase difference. Okay. Or you can use t over period times 2 pi. The t over period, you will get half. You definitely get half. So you end up getting pi radian. So in exam, any type of oscillation, how to get phase difference, draw the graph. The graph normally given, then you can use the formula to find the phase. Any questions from here? No questions, Okay. Okay, so that's phase difference. Two oscillations that have the same frequency but different phase is said to have a phase difference. Phase difference expressed in degrees or in radian, preferably radian. Preferably radian, 0 to 2 pi. If the phase difference is 180 degrees or pi radian, then the two oscillations need to be antiphase. Okay, they move in opposite direction. Okay, yeah. If the phase difference is 2 pi radian, they say it to be in phase. Okay, so this is the introduction of oscillation. Okay. Okay. So now let's come to the real part of the topic. We have many types of oscillation. Okay. So oscillation. But there is some group of oscillation quite special. That group of oscillation, we name it as simple harmonic motion. Okay, we call it simple harmonic motion. This is a type of oscillation. This is a type of oscillation, unique type of oscillation, where the acceleration of the particle is proportional to the displacement, but in opposite direction. Okay, what is meant by this? But first, try to put in your mind, oscillation, like you have a big group of oscillation, a small subset, small subset, a small group of that. This is oscillation, all type of oscillation. Small group of oscillation, that is called simple harmonic motion. Okay, it has a certain unique feature. Okay, our entire discussion in our class after this is about this SHM, this unique oscillation. Okay, simple harmonic oscillation. Remember, all SHMs are oscillation, but not all oscillations are SHM. Okay, like oscillations like Malaysia, SHM is like Selangor. Okay, Malaysia, Selangor is part of Malaysia, but Malaysia is not in the Selangor. The SHM is the subset of oscillation. Okay. Okay, now go on top here. This is the definition for simple harmonic motion. What is meant by simple harmonic motion? Okay, remember by heart this one. Simple harmonic motion is a type of oscillation where the acceleration of the system is directly proportional to the displacement. Okay, and always directed towards an equilibrium position. That is SHM. Okay, what is meant by this? Okay, let me go to the whiteboard to explain this. Okay, and acceleration is proportional to the negative x. Okay, to understand this, let's go to the whiteboard. Okay, we go to the spring. We go to the spring. Spring, this is equilibrium. Okay, this is equilibrium position. Okay, spring is equilibrium position. Okay, so let's say you extend the spring until certain displacement x. Okay, x. Let's say you displace it further. Displace it further to x2. This is x1, this is x2. Okay. What happened to the force when you let it go? This is your force which is pulling it back. F2, when you let it go, this is the force it's pulling it back. Let me label it as F2. Can you now tell me, F1 bigger or F2 bigger? X2 is greater than X1. So therefore, F2 greater than F1, correct? F2 is greater than F1. So tell me, when the particle is, when you let go the system, which going to move forward with a greater force? Which going to move forward with a greater force? F2 going to be the greater force, right? Hooke's law, right? F equals to kx. So F2 is greater. If F2 is greater, which particle going to accelerate greater forward? The A2 greater or the A1 greater at the moment of release? Who's greater?
Moment of release.
At the moment when you release it. When you release it.
F2.
So A2. A2 is greater than A1. Correct? So for this system, what we conclude? When x is greater, when x is increased, x means the displacement line. The displacement get bigger, the force get bigger, so the acceleration get bigger. Correct? So we conclude that the acceleration and displacement is found to be proportional to each other. A is directly proportional to the displacement. You displace further, the acceleration get greater. Okay, but you see the displacement. Displaced down is said to be negative. displace up say to be positive. Okay. So the displacement was negative. The displacement is directed downwards. Okay, displacement directed downwards. But acceleration, which direction? Acceleration, which direction? See, I pull the mass down. Displacement is downwards. When I let it go, acceleration, which direction? Upwards or downwards? Anyone? The acceleration is
Upward.
upwards. The acceleration is upwards. So when the displacement is downwards, acceleration is upwards. So we need to correct this. A is proportional to x, but it in opposite direction, negative. Okay. So A proportional to negative x occurs to this spring. So this spring categorized as a simple harmonic motion. Okay. So spring oscillation is a type of simple harmonic motion. Why simple harmonic motion? Because the acceleration of the system is directly proportional to the negative of the displacement. This is called simple harmonic motion. Okay. So what is meant by simple harmonic motion? A type of oscillation where the acceleration is directly proportional to the displacement, but it acts in opposite direction. Or you can say acceleration directly proportional to displacement, but act towards a fixed point. Okay, the acceleration always direct to fixed point. Okay, let's say the spring is compressed here on top, compressed. So the displacement going to be positive or negative? Displacement is positive. How about the force? Force now directed downwards, it's because under compression state. So force going to push down. So force consider or the acceleration is considered negative. So the direction always different. So spring is an SHM. Okay. SHM means when the particle move away from origin, the force we try to restore it back must get bigger. Okay, again, if it's an SHM, when the displacement of the oscillation increases, the force which tried to restore it back must increases. Okay, so go back to the thing. So recall back again. See the read back. Try to understand what is SHM. What is SHM? Type of oscillation where the acceleration is directly proportional to the displacement, but direct towards a equilibrium position. Or you can say act always act opposite direction. Always act opposite direction. Okay, opposite direction. You see that. Okay. So yeah, if I want to draw a graph, or I can show this graph bottom here, the acceleration and displacement will looks like this. Okay. So acceleration is positive, displacement is negative. When acceleration is negative, displacement is positive. It's an SHM, simple harmonic motion. Okay. So let's strengthen the idea. Now I'm going to show you a different system. Let's figure out, is it an SHM or not an SHM? Okay. Go back. Now we're going to talk about pendulum. Pendulum swings here and going further up. Okay. You want to check and go and back, move back and forth. We know this is an oscillation. This is oscillation, But is it an SHM? Is it SHM? How to check? So when the displacement, this is displacement x1, okay, this is the displacement x2. What you need to prove is when displacement increases, the force try to restore it back, try to pull back. Is it increasing or decreasing or no change? Doesn't change, never change. That's what you need to decide. What do you think? To find when the pendulum is moving away, the force is she's trying to pull it back, increasing or decreasing?
Really?
Okay, for this, let's withdraw all the forces acting on the system. I take the x1 first. So let's say I draw the pendulum here, tilted. Let's say make an angle from vertical theta. Okay. Can you tell me what are the force acting on the pendulum? Mg acting down. What else? Tension acting diagonally. Okay. So the theta here vertically is T. Okay. So what force pulling it down? So here also theta. This is 90. This is like 90 degrees now always. Okay. What force pulling it down? What force is directed here? This way. Which component? The tension or the mg pulling it down? The mg, right? Mg tension and the force is like 90 degrees now. 90 degrees. Okay. 90 degrees. So the force pulling it down is what? F is equals to what? You need to resolve the mg. Mg you resolve to the direction of the force. Cos theta or sin theta? You open the angle or close the angle?
Sine theta.
Sin theta. So F is mg sin theta. Okay. So the net force pulling it back, try to restore it back, is mg sin theta. Okay, now tell me, when displacement increases, the force trying to restore it back increases or decreases? This is the formula we rely on. When the x increases, what happened to theta? More higher. You see the theta is theta 1, here theta 2. So when displacement increases, theta increases. When theta increases, what happened to the sin theta value? Sin theta here, sine graph. Sine graph goes up, come downward. 0 to 90, right? So when the angle increases for the first 90, the value also increases. So conclusion is what? When the displacement increases, the force increases or decreases or no change? Because theta increases, sin theta increases, so force is also increases. Therefore, pendulum categorized as SHM. Yes, correct. The pendulum is an SHM. Okay, label it as SHM, simple harmonic motion. Why label it as SHM? Because the acceleration is directly proportional to the displacement, but in opposite direction. Okay, this rule obeyed by this system. So this is an SHM. Any idea? You don't understand, guys? So you have to resolve this to check displacement rise, force rises, then it's going to be an SHM. Okay. Okay, let me go to another system. Okay. You have like this track like a V shape. You have a pendulum here. Okay, the pendulum move back and forth like this. Okay, like this. Okay, moving like this. Okay, it was tilted at the same angle. Okay, so it's moving up, down and up, down and up and down, and so on. This oscillation. Now the question is, this oscillation, is it an SHM? Okay, 1 minute for you. Think, is it an SHM? If it's an SHM, the acceleration must be proportional to negative of the displacement. When displacement increases, the force tried to restore back must be increased. Therefore, acceleration increases. Then we conclude it's an SHM. Okay. So try to test for me. And the displacement increases. And the displacement increases. Okay. This is the first position. And let's say the ball is here. This is next this x1, this x2. When the displacement increases, the ball going further up, the force trying to restore it back. Is it increasing or unchanged or decreasing? Okay, draw the free body diagram for the pendulum. Okay, let's say I put the pendulum here. I mean the ball here. Can you draw the free body diagram for the ball? So what are the force acting for the ball? Force down is what? Mg acting down. The force acting up is what? Your normal force. The restoring force we are looking for is this force. Okay. Okay. And for a short distance, the angle here we know is what? Angle here is theta. So can you tell me the restoring force equals to what? The force is equals to what? Again, the mg, the force pulling it down is what? It's an inclined surface, inclined surface. What force pulling it down? The mg resolve horizontally, right? So it'll be what? Mg cos theta or sin theta?
Sin theta.
Sin theta. Yes. So the force is mg sin theta. Again, like a pendulum. So now tell me, is this an SHM? When the displacement get bigger, yeah, put here, when x increases, what happened to the force? Force, is it increasing? Is it decreasing? Or no change?
Constant.
Constant. So theta doesn't, because theta doesn't change. Theta is always the same. So force doesn't change. So in this case, when displacement rises, the force is constant. Therefore, this is not SHM. Okay, this is not SHM. The acceleration of the system not directly proportional to the displacement. So this is not SHM. Okay. So not all oscillations are SHM. Only some are oscillation or SHM. What is meant by SHM? What is meant by SHM? SHM is a type of oscillation where the acceleration is directly proportional to the displacement and directed towards an equilibrium or in opposite direction. It's how the graph should look like. Okay. Okay. So another one. Go to another one. Tell me, is it SHM or not? Okay. SHM or not? Okay, I'll leave it to you. You have one tube, U shape. Okay, you have a liquid here. You have a liquid here. Okay, what do? You blow. You blow the right opening. Blow it until what happened? The level rises here. The level decreases here. Okay, level rises and level decreases. Then you let it go. What happened? The water will start to oscillate up and down, both sides. Okay, this up, this down, then the other way around. This will down, this up. It will going to oscillate, right? Maybe some of you have done this before. Okay, blow at one edge. Okay, blow at one edge. Let's say this is the center equilibrium. This is the center equilibrium. Okay, this x, this is your displacement. Okay, you blow more, you can increase the displacement. You blow more until down, the displacement get bigger. Huh? So now tell me, is it an SHM? Is it an SHM? Is it greater the displacement, the force trying to restore it back get bigger or not? Is it getting bigger, getting smaller, or not changed, unchanged? What do you think? 1 minute for you to think. Come on. You blow at one corner. You blow at one corner, you blow until the maybe a small displacement, 1 centimeter, you let it go, it oscillates. Then you blow further, 2 centimeter displacement, you let it go, it oscillates. When you blow further down, you let it go, the force which trying to restore it back, is it increasing or decreasing? What force trying to restore it back here? Okay. What force trying to restore it back here? The water level is like this. Okay. This, the water which is the on top, the water is on top here. The weight of this water, the weight of this water on top here is the one like acting as the force downwards. Okay. When the level of water on top is increases, so the force which is pulling it down, which is the weight of the water on top, which is pulling it down, increases. So when displacement increases, the force is increasing, decreasing, or no change? It's increasing. And the force is increasing. You blow further down, the amount of force acting on top here at the equilibrium state line, at the level, same level, is more. So more the greater the mg, the force pulling it down is greater. So the acceleration get greater. So this is an SHM. This is, of course, is an SHM. Okay. So any questions, guys, from here? What is meant by SHM? Okay. So spring, pendulum, this tube, it's all SHM.
So is it because there is more mass at the other side when it is oscillating?
Yeah, more mass at one side. So the mass is the one causes the weight of the mass above is the one causes the force pulling it down. So therefore the force increases. Okay.
Yes.
Because when you blow, you blow the water more higher here. You let it go, you can see the water going to drop a lot. Right? The force which is pulling it down greater because the extra mass on top here, the mg of that water is the force pulling it down. So more greater the water on top here, more greater the mg, more greater the force pulling it down. So it's an SHM. Okay. Okay. So any questions? No questions, eh? Okay. Now we go back. Okay. So let me, before, this is how the spring at the bottom here is moving. It's an SHM. It's oscillating. Okay, it's oscillating. Okay, the black arrow on top is your displacement x. The green arrow at the center is mentioning about the velocity it's moving. And the last one, the rate, is the acceleration. Okay, now you see the black arrow and the rate. The what do you call? The displacement and the acceleration. You see the arrow? The both arrow getting longer at the same time. At equilibrium, both arrow is very small. But when it comes to the edge, both arrow getting longer. But you can see the direction of the arrow is opposite. Okay. You see now the black arrow on my right. On my right. Now let's say it's moved to the right. Wait for a second. The black arrow on my right is directed to the right. Again, when it flips to the right, you see the acceleration directed to the left. This is SHM. The acceleration is directly proportional to the displacement, but you see opposite direction. The red arrow and the black arrow in opposite direction. Okay. We will come back to the green arrow, the velocity. Okay. Velocity, is it make sense? Okay, let's go a little about the velocity, the green arrow. Velocity become maximum at point or at the maximum displacement. When the spring, the particle moving up horizontally, where the spring moves faster, when it's at the equilibrium or when it's at the edge, at the displacement, maximum displacement. At the equilibrium, right? At the equilibrium, the spring will move faster, you know. When you come to the edge, because it slows down, the speed will drop to zero. Okay, so that's why the green arrow is always become longer at equilibrium. See the green arrow at equilibrium is longer. When you come to the edge, the velocity becomes zero because it's about to make turning. I think Form 5 in additional maths you learn a topic, motion in a straight line. A particle when make a turning, the velocity become zero. The velocity will reach zero at that moment. Okay. So that's this animation trying to explain. This is an acceleration directly proportional to the displacement, and we are adding another one quantity, velocity. Velocity become maximum at equilibrium. Acceleration become maximum at where? At equilibrium or at the maximum displacement? The acceleration. The acceleration become maximum at which point? At equilibrium or the maximum displacement? At which point the red arrow become longest? At the edge. At the edge, acceleration is maximum. Okay. So students, any questions? Okay, now what we're going to do, we're going to, let's say you have a pendulum, you take a stopwatch, you start the stopwatch when the pendulum is at the center and the pendulum is swinging. Okay. Now what we want to do, we want to find when it displaces for a displacement of x, the total displacement is, let's say, x naught. Okay. For a one particular instantaneous point displacement at this point, what is its velocity? What is its acceleration at this moment? We're going to discuss. Okay, at any point, at any random point. What is its velocity? What is its acceleration? Okay, we're going to discuss. Okay, first, if the pendulum is at the center, time zero, okay, and it swings to the right first, right, we consider as positive. Then after that, it swings back to the left. Left is negative. If I draw displacement versus time, how this graph looks like, I give option. Is it going to be a sine? Is it going to be a cos? Is it going to be a negative sign or negative cos? Time starts 0 in center. Time starts 0. T starts 0 when the object is in equilibrium. It's moving to the right first, then come back to origin, then moving to the left and come back to the origin. If I want to draw x versus t, how the graph trace looks like? Sine, cos, negative sine, negative cos. To the right, consider positive. To the left, consider negative. Anyone?
Sine.
Sine. Because when the time 0, the point is here at the center. Then it becomes positive displacement for a quarter period. So it goes up. Then half period, it was come to 0. Then immediately go to the left and come back. So it's a sine. It's a sine graph. Okay. It's a sine graph. So we're going to create a formula for this. We're going to create formula. Okay. Now I want to write a formula for this. Formula. What is the formula for displacement? Can you write formula for this sine graph? X equals to, last time in your form 5, how do you write formula for the sine graph? You write sine, you write the peak value here. So here we write x naught. X naught is the maximum value, maximum value. Sine. Here we write in terms of time. How do you write angle in terms of time? I want the angle to be in terms of time. How time and angle related? Omega equals to theta over t, right? So angle and time related. So how do you write theta? Omega t. So yes, omega t. This is the formula for displacement. The first formula. For what? Displacement. Okay. So for now, what is the use of this formula? At any given time, let's say the period of this oscillation is 2 seconds. Let's say I plug in, I want to know what is the displacement of this particle when the time is 0.1 second. When the time is 0.1 second after it's launched, what is the displacement of the particle? I can use this formula. The time I just slot in as 0.1 second, omega, I find the omega first because 2 period we know, so we can find the omega. X naught, we put the maximum displacement, how much, the amplitude, we put it in, so we can find the displacement. So now we can find the displacement of the particle at any given time. Okay. So if the time start from the center, if the pendulum start from the center, the displacement formula is definitely going to be sine. So the front, we put the maximum value, x naught, and the angle, we put it in terms of omega t. So we get the formula for displacement. Any questions? Okay. Now, let me ask you, if the time started at the age, I start time at the age here. You see that at the age, the time 0 started at the age here. How the displacement graph for this going to look like? Sine, cos, negative sine, negative cos. Time start from the age. Time 0 is at the age, when it's at the age. So that means the pendulum move like this, come back here. Anyone? How this graph looks like? Time start at the age. Displacement versus t.
Cos graph.
Sine, cos, negative cos. In the time 0, the displacement is maximum, right? So where the graph going to be? You start from the top. Then quarter period, you come to the center. come to the center, then become negative, then become positive, then go up. So how's the graph? It's going to be a what graph? It will be a cost graph. And the time start at the edge. Then what is the displacement formula will be? Anyone? X equals to X naught cos omega t. This is the displacement formula for a particle when the time starts 0 at the edge. Sine is the displacement formula for the particle, the time starts 0 at the center. So the displacement formula varies, not always same. All depend, you need to check, is it time at the equilibrium or time at the edge? Time start at the edge. If it's time at equilibrium, fine. If the time start at the edge, cos. Okay, class? Any questions? Okay, so this is today's lesson, just introduction of oscillation. So what you learned today, you learn about what is meant by SHM, phase difference, then the, what do you call? Then the definition. Any questions? Okay, so try to understand this. We will continue on Friday, Friday 10 o'clock, 10 to 1. We continue this SHM as a replacement class. Okay, so I stop here. Okay.